So what is that research concern? And these are some graphics thanks to Kate Gordon, who's gained a lot of fame because of her work at the intersection between faith communities, scientific communities, and efforts to communicate climate science effectively to audiences, some of whom were very skeptical. We have relied as a civilization on the fact that we've had an extremely stable climate during this period called the Holocene for the last 10,000 years. It has allowed us to establish agrarian agriculture, and that's what's meant by this very stable horizontal line. There's been fairly little radical environmental change during this time period. And of course, superimposed on top of this long period of undisturbed climate are weather fluctuations, and those are important. And to give you some sense of what this stability has meant for human civilization, this is a really great movie of the world civilization sort of booting up. And because I don't want to play this all in sort of super slow motion, I'm going to sort of start skipping to the good bits. But you can see civilization cities spring up all over the Middle East. As we start to get into the Iron Age, you'll see them boot up in Greece, also in Asia, and in Central America, and then start to move into Europe and so forth. Human civilization has relied on the stability provided by our climate to pull off this explosion of cities, which have been key sources for human creativity, along with their interactions with the surrounding populations. So what happens if things begin to change quickly? Well, then the premise around which we've sort of structured our civilization on the back of a very steady climate envelope, that assumption is now violated. And not only if you blow up that period where things are changing rapidly, the weather comes along for the ride. And we are increasingly seeing changes in extreme heat, extreme rainfall, that I'll come back to a little bit later in this talk to amplify how weather is coming along with the
okay, I've got it up, Golden
envelope. And both are now changing in ways that are fortunately historically unprecedented. So there are multiple indicators around us that the climate has begun changing fairly appreciably. Most of the warmest years recently have been in the 21st century. We're in a time period now where those of us who are teaching, who are older than 35 or so, are teaching students who've never lived in a normal climate. So imagine, staring out at your classroom at the student body in front of you, and all of them are living, literally are students of the Anthropocene. They've grown up in a period where California's climate is quite a bit different than it was during the gold rush. And the driver for this, and I'll be happy to entertain questions about why we associate these two things with each other, but what the climate community is now firmly convinced of, for a very good reason, is that the element that's sort of forcing all of this change are rapid rises in greenhouse gases. Now, greenhouse gases are a good thing. They make the Earth habitable. If we didn't have a greenhouse effect on Earth, the Earth would have the same mean temperature as the moon. And that mean temperature, that average temperature, is below the freezing point of water, which would not be good for us. So the greenhouse effect creates a blanket, and the Earth and the moon receive almost exactly the same amount of sunlight from the sun. They reflect almost the same amount of sunlight back to space. Very similar astronomical bodies, but the Earth is above freezing for water, the moon below. And it's thanks to these greenhouse gases. But you can also add greenhouse gases to the atmosphere, and this graph illustrates that very nicely. This is the Keeling curve developed by a scientist at Scripps. He started making measurements in the 1950s and really nailed down how to measure carbon dioxide very accurately. And I should date myself by saying that this time span, of course, is just 60 years. It's a human lifetime. I'm now revealing my earlier self here in swaddling clothes on the left. This is when I was 8 months old, and in my current instantiation. And this is a a 25% increase in carbon dioxide in a single human lifetime. So that's how rapidly we are perturbing the chemical composition of the Earth's atmosphere. We're changing it on time spans that now are considerably compressed relative to a human lifetime, and in fact, radically compressed compared to the geological record. So one of the things that my group and I did 7 years ago was to ask, can you see the effects of this on the Earth's surface? Can you see the heat being radiated from the atmosphere back down to the surface increase in concert with rising carbon dioxide levels? And thanks to investments made by the Department of Energy that Professor Chu oversaw during the Obama administration, we have a superb record of observations that we can use to make this connection. So let me run the movie for you. This is from Oklahoma. This is rising CO2 concentrations and rising levels of heat being emitted by the atmosphere down to the surface. And then the movie will replay for Barrow, Alaska, a much more pristine environment, again, rising CO2 and rising greenhouse effect. So there are a couple of things going on in this movie. One of them, you notice an upward trend that's due to increased load of carbon dioxide in the Earth's atmosphere due to mankind's activities. You'll also notice a sawtooth pattern. That's due to the annual cycle in photosynthesis and respiration by plant life in the Northern Hemisphere. We were the first to both demonstrate this greenhouse effect directly from observations, but also to measure this sort of natural fluctuation in the greenhouse effect due to photosynthesis. So again, that's an ecological benefit from which we all greatly enjoy the fruits of nature because of the productivity of our agricultural cycles. So as I mentioned, we're changing the chemical composition in ways that are pretty radical. The last time we had CO2 concentrations this high was 3 million years ago. And so I've made an illusion that I test on my students in class, which one of them who are now were born after this movie came out, understand the reference to Back to the Future, but the idea is that our automobiles are literally time machines, and they're taking us from the state that existed in all over the world just before the invention of the steam engine, and they're taking us backwards in time, effectively. So it's taken us 300 years to replicate 3 million years of of evolution of the Earth's atmosphere. And that's a compression of a factor of 10,000 in time. That's how much we've accelerated the chemical composition change in the Earth's atmosphere. If we keep this up, we're going to be hitting acceleration factors of 100,000 by mid-century. So that's a pretty radical acceleration of change in the climate system. And the question is, what's going to happen in the future? So what the international climate community has done in concert with the UN and the World Meteorological Organization is to commission assessments that we distribute to governments every 6 or 7 years to help them make decisions. And ideally make decisions where we can tell them what they should and should not be confident about. And so we're not doing research. It's like a meta-analysis that you would do in medicine. We are assessing the literature and then deducing from it what things we do and do not know with some confidence. But the IPCC does not do research. And it's been going on now since really the first assessment was issued a little over 30 years ago in 1990. I've done 3 of these. These are the picture of my author team from the 6th assessment. I'm not going to do any more. I think it's very important to increase the diversity of the author team and also to ensure that other voices which have historically not been represented in these assessments have an opportunity to join. And so for this reason, the 6th was my last. But it was an amazing process. So there were 230 authors from 65 countries. We're getting better about at least the gender balance, but still have some way to go yet. One of the things that I'm particularly pleased is that 1/3 are new to the IPCC. So this means that there's a good turnover rate. For those of you who are used to writing papers, particularly in the scientific literature, this is peer review on steroids. So we got close to 80,000 reviews that we had to answer in writing. All of that's cataloged, and it's going to be shared with the public. So we couldn't be sarcastic in our responses. We had to answer very respectfully, even comments we got from climate skeptics, and they most definitely weighed in on this assessment, and countries. So the governments from the member states of the UN appointed reviewers. This includes reviewers from Saudi Arabia and Russia and the US and China and Australia, which is a major coal producer. They all got a chance to weigh in on this assessment. And what I'm going to show you is the distillation of this gigantic piece of work in what's known as a summary for policymakers. And even though it's designed for policymakers, the graphs are a little bit technical, so I'll step you through them. But this summary for policymakers was reviewed literally sentence by sentence by approximately 50 governments in the UN General Assembly. So these governments cannot claim ignorance of climate change because their own representatives approved this document. Literally, they voted on every sentence in it. And that process took slightly over a week. So ignorance is no excuse here. Everybody knows what I'm going to show you right now. Okay, so what the IPCC has said is that we're seeing a period of very rapid change, and it's intensifying. And it's unprecedented in thousands of years. And now this is where the graph, I'm going to start showing you these graphs. Remember, these are aimed at policymakers, but perhaps for the environmental ministers. That might be a more generous way of thinking about this. The graph on the left shows you the anomaly in temperature over the last, since the last 2,000 years. And it's relative to a climate mean. You can see that over most of that time period is very steady, and then it began to very rapidly rise in the last couple of centuries. And you can then ask, well, what does this due to? There are many ways in which we try to tackle this problem, but one of them is by creating a synthetic Earth in a computer. And we can take humanity out of that model and then emulate what would have happened in the 20th century, where only volcanoes and the sun acting in the climate system. And that's this green trace here. And you notice that by the end of the 20th century, beginning in the 21st, it is several standard deviations away from the actual climate record. You cannot explain, the black line here is the actual data. You can't explain the actual data in a world where you omit human-made greenhouse gases. This is one of me, I wouldn't believe this myself, and I've led the design of a couple of major climate models in this country. There are many other lines of evidence that support this finding. So it's indisputable that we're, and by the way, I should mention that this part of the talk is sort of the darkness before the dawn phase, so bear with me. It's tough to talk about climate change without dealing with the reality of the impact that it's having. I am an optimist, at least on alternate days of the week, so let me get through this part of the talk and bear with me. But we need to sort of, these are the sobering findings that we've presented to the world's governments for them to think about. There are many more extremes than there have been in the past. And we're confident that let me go back. Yeah, and we're confident that humankind is the cause of all these changes. This graph is, see if I need this to advance. Come on, here we go. What this graph shows you is the total change in temperature and then the total influence. And you'll notice that those two bars are essentially identical in height. Again, indicating that the recent climate record, we know what volcanoes have done to the climate record over the last roughly 150 years. Thanks to Galileo, we know what the sun has done to the Earth's climate since the middle of the 17th century. Neither of those will explain what we're seeing currently. And we know those to some degree of quantitative precision now and accuracy. Climate change is affecting every region on Earth. And I'm going to show you a graph that looks vaguely like a map. This is how the IPCC looks at the world. So we've divided the world into 55 different countries. This is North America, this funny bow-looking shaped on the object on the left. The upper part is North America. The lower part of it's, of course, South America. Then we have Europe and Africa in the middle, and Australia, New Zealand, and so forth, and the small islands in the Pacific on the far right. The red color means that there have been highly confident, there's a high degree of confidence that extreme temperatures increased in 47 out of 51, 51 out of the 55 countries or regions on this graph, meaning it's essentially worldwide. So this is pretty much a universal phenomenon in terms of the impact on temperature extremes. And then one of the other things that we do in as part of this process is we look forward. So the same models that we use to interpret the historical record and to try to understand whether to attribute what we're seeing to natural causes or to the influence of humankind. We can take those exact same models, and by the way, these models are based on, let me just put it this way, if you're wanting to get on board an airplane, which these things are now designed using the same equations of motion almost entirely in a computer, if you're wanting to get on board an airplane, then you should at least give climate models a reasonable fighting chance, because it's the same equation set at the 0th order. We solve those equations forward in time and ask what's going to happen in the future. And what we're saying, and some climate community is saying this very loudly, is that we should really try to avoid warming the planet more than 1.5 degrees Celsius, which is a little under 3 degrees Fahrenheit, relative to its temperature before the invention of the steam engine in sort of pre-industrial times. But we say this in we cannot be policy prescriptive. We can be policy relevant. And so one of the things I'm going to show you is that we run a variety of scenarios. One of them where we really strongly mitigate greenhouse gas emissions, and another, and ranging all the way up to scenarios where we barely lift a finger to try to mitigate climate change. And we hand that basket of results, of projections, to the worldwide governments who've commissioned this report and ask them to pick one. So this statement is based on running a variety of scenarios for the future. And I'm sorry, this is a horrible graph, but let me walk you through it. The vertical axis on this graph is gigatons of carbon dioxide per year. So we're currently emitting 40 gigatons of CO2 per year. This is off scale compared to any other industrial chemical that we use in bulk, ammonia, chlorine, you name it. This is an order of magnitude bigger than any other industrial chemical that humanity uses currently. It's a titanic amount of mass of CO2 that we're injecting into the Earth's atmosphere. And then as we play out the string over the 21st century, here's the scenario where we don't really bother doing much until late in the century. And SSP stands for Shared Socioeconomic Pathway. And then the number at the end indicates how much we've budged the energy budget of the climate system. And it's in units of watts per meter squared. I won't go into any further detail there. It's a unit by which we denominate how much we've altered the greenhouse effect. And you can see that the scenarios then step down from being this dark red to a slightly more friendly red to yellow to blue. And this lowest scenario, the SSP 1.9, is where we drastically begin to curtail emissions. In fact, have reached zero emissions by the year 2050. And then through technologies that we are again beginning to explore through the Department of Energy and other federal agencies, hope to begin removing carbon dioxide from the atmosphere by the middle to late part of the 21st century. There's an intense debate, and we are aware of it and are sensitive to it, between those in the climate justice and the environmental communities are very concerned that direct air capture, which is what these scenarios rely on, provides a fig leaf for continued use of fossil fuels. We understand that. Unfortunately, the climate community now thinks that we reached a point where we will have to invoke those technologies in order to avoid dangerous climate change. We have no choice except to explore whether or not we can do direct air capture at scale. So we ran 50 climate models worldwide on these 5 scenarios. That's generated literally petabytes of climate model output, the largest assemblage of climate model data. It's all in the public domain. I could show you, if we had time, how to run a browser command and start downloading it to your laptop. All of this is freely available. It's a worldwide resource. People are also using it now to make planning decisions. This is a resource now for city, county, state, national planners who are using these scenarios to figure out how to adapt to climate change. So what do these scenarios show? And the main thing I want you to just focus on is this vertical axis, again, is in temperature. And the main thing I just want you to notice is as we go from scenarios where we strongly mitigate emissions and barely remain under 1.5 degrees, this is the SSP 1.9 scenario. And we sort of continue to something that's what we hope is actually more drastic than business as usual. Business as usual is probably centered around here, SSP 7.0. We've warmed the planet by 3.5 degrees Celsius. A little under 7 degrees Fahrenheit. Now, I mean, we all know that that's not a big temperature swing. But the Bay Area just went through a temperature swing bigger than that between the weekend and today. Right? So that doesn't seem like such a big deal. But this is the global mean temperature. And the way that plays out, of course, is that the ocean is the big thermal reservoir in the system. And these effects are drastically amplified over land surfaces which have a much lower heat capacity. So the small magnitude of these numbers is a little deceptive as to how big an impact we will see on terrestrial ecosystems and on land where most of humanity lives. In many cases, this is somewhat of a you broke it, you bought it proposition. Carbon dioxide stays in the Earth's atmosphere as an effective chemical lifetime of about 120 years. So we will be living with the legacy of this for a long time. The ocean takes 3,000 years to equilibrate to what we've done to it. So again, it will be warming for a very long time. I mean, the distance between now and when it will cease warming is the distance between now, roughly, and the Bronze Age. So that's a big gap in time. However, the things that can be stopped if we take concerted action. And at the end of my talk, I'm going to talk about the many ways in which that action is beginning to happen and beginning to bear fruit. Sorry for this graph. This is just to illustrate this. I mentioned extremes earlier. I want to the main thing I want you to do is count dots. So this shows you in what 50 years events look like in a world where over a 50-year time period, in the late 19th century, a 50-year heat extreme would occur once in 50 years. No surprise, that's why we call it a 50-year event. That same 50-year event becomes an annual event if you allow the planet to warm by close to 4 degrees Celsius. And these events are starting to cause heat trauma. And in fact, this is now recorded. It has been recorded in parts of the world like India and the Middle East. This is coming for portions of the American South. The effects of these kind of heat extremes. Ocean levels will also continue to rise. And as you can see, the ocean level sort of scales and increases with increased emissions. We are still in the process as a scientific community of figuring out the big joker in the deck, which are what are the Greenland and Antarctic ice sheets going to do? So currently, sea level rise is made up of 3 components, a third, a third, a third. Water expands when you heat it. And so that's very simple. It's just based on the equation of state of water. So we've been heating the ocean, it expands a little bit. We've also been melting land glaciers. That's currently a third of sea level rise. And we've been slowly but surely getting Greenland to shed ice. I know Antarctica is in on the game too. And that's another third of the total budget that we're seeing for sea level rise, which is on the order of about 1 millimeter per year currently. And a millimeter is the thickness of a dime, doesn't seem like very much. But you allow that to accumulate, and you're looking at 0.5 meter by the end of the century. But the joker in the deck is what Greenland and Antarctica might do. And there are ways in which those ice sheets could greatly amplify sea level rise. Greenland is equivalent to 7 meters of sea level rise if you were to somehow get it to all fall into the ocean. Antarctica is 70 meters, 70. And we don't think this is going to happen on any timescale in the near future. But if you look at some of the more radical projections, again, this is under business as usual, for 2300, we're talking about inundating, well, I mean, San Francisco would be a completely different city with 7 meters of sea level rise. It would just be a radically different city. So we hope this scenario does not come to pass, but we can't rule this out. And roughly a tenth, 600 million people live within 10 meters of the ocean surface. So this is going to, these scenarios on the right would be pretty game-changing for large portions of humanity, and especially the world's great cities, many of which are, of course, located close to the ocean. London, which has constructed the Thames Barrier, as you know, on the Thames between it and the North Sea, plan to operate that facility every year or two. They're now operating it multiple times a month, and they're going to have to build a second Thames Barrier, if they're not already starting to do so, to ensure that London remains safe from the incursions from the North Sea. So the good news is that if we start taking on what's needed to address climate change, this comes with a variety of major, tangible, immediate co-benefits. And let's talk about air quality, because this is a picture taken from an Asian megacity. The World Health Organization estimates that 6 million people a year die from particulate inhalation from the combustion of fossil fuels and biofuels for cooking stoves and other things. That's equal to the worldwide toll from COVID that we just experienced in the last 2 years. But this is every year that people are dying from inhalation of soot, from diesel and so forth. And this number was published a couple of years ago. I'd be happy to provide the source if you're interested. That's one of many benefits that we realize from getting off of fossil fuels. And the United Nations and the assessment reports have now, for the first time, begun cataloging these co-benefits, what are known as sustainable development goals, in order to clarify that solving climate change doesn't yield a benefit 100 years from now. It yields tangible, environmentally just, climatically just benefits essentially immediately. This is one of so I'm almost done describing kind of the doom and gloom part of it, or going to the doom and gloom part of this lecture. But we're essentially on a straight line path, and we have to make a choice as to where we stop on that path. This is the amount of CO2 that's been emitted since the middle of the 19th century, again, expressed in this somewhat unfriendly unit of gigatons of carbon. And this is the change in temperature. And you'll notice that over the historical record, both the data and the climate models are remarkably linear. And then the question comes, well, fine, okay, if it's linear in the past, and the models projected this linearity persists in the future, where do we stop on this path? And this is a choice we have to make. So the climate community is now saying, we've run out of road to kick the can. We have stalled for too long, and we must now make some difficult choices. And the IPCC has begun ringing the alarm bell louder and louder. There was a report issued before the main assessment that just started coming out last year on 1.5 degrees, now to stay underneath it. It said we scientists will start to lose predictability once we get above 1.5 degrees Celsius for a variety of reasons, not least of which is the fact that our models don't include human behavior. And that's likely to get start doing some funny things once the planet gets appreciably warmer. But we're worried about not being able to make terribly accurate predictions once the planet gets warm enough. This is an older figure, but I raise it to point out that the scientists love to talk about uncertainty, because uncertainty is what we focus on reducing, and we worry about reducing the uncertainty in our understanding of how nature works. That's critically important. Please don't get me wrong. And for those of you who want to get into the climate field, there's lots to do. But the one thing I think that's critically important to understand is that what happens at the end of the 21st century is dominated by the choices that we make between now and then. The uncertainty in our climate models and our understanding of how climate works are not the dominant source of uncertainty and variance is another word for that. Human choices are really, there's a fan of possibilities, as you could see, places where we stop, and that choice is ours to make. So this process is led by some extremely dedicated scientists. This is the co-chair of Working Group 2, Deborah Roberts. Working Group 2 deals with the impacts of climate change on society and the environment. And she says, the next few years are probably the most important in our history. We have an opportunity, but we also have to seize that opportunity. Valérie Masson-Delmotte, who was the co-chair of Working Group 1, she was the person to whom I reported as part of the IPCC. She says the good news is that there are a lot of actions, but they need to accelerate. And this is, she was being somewhat, she was being very careful with the words here, but yes, we are, just as we accelerated climate change, we now need to accelerate the solutions to climate change in an equally radical way. So now I want to turn to the part of the talk where I see, some rays of hope, quite a few rays of hope. As I mentioned, I'm based in the East Bay, and there's a consortium of cities all up and down the East Bay that have formed a Green Jobs Consortium, and they are putting people to work, re-insulating homes, installing electrical infrastructure, removing inefficient appliances, installing solar, and this runs, I think, all the way basically from Richmond on to Fremont or something. It's a pretty big and extensive network. Solar is coming online really rapidly. So this shows you that solar is literally growing exponentially, which is quite phenomenal. We've reached this year 700 gigawatts of installed solar worldwide. Wind is comparable. So it's 700 to 800 gigawatts of wind. Those two clean energy sources combined are now equal to 1/10 of the 17 terawatts of energy that humanity consumes. So we've now, because of this exponential growth, managed to displace 10% of, whatever legacy energy sources were sitting there. This is good news, and exponentials have a habit of catching up with you. So this is a really phenomenal development. The other development is that electrical and wind are now the new energy sources of choice because they're cheaper. They're preferred by ratepayers because they are less expensive than legacy energy sources. I've been told by people who monitor the California energy markets that there are times in the summer when the energy rates in California effectively go negative because of the amount of power we're able to produce through renewable sources. So what this shows you basically is, these solar and wind now plunging below this big black line, which is what you would get from natural gas, which is really where you want it to be. You want renewables to be cheaper than the legacy fuels. And I'd be happy to talk more about methane, but methane, the premise that methane is a clean fuel is predicated on some assumptions that we could come back to during Q&A if you wish. It's unfortunately not quite as green as some people would like to make it seem. We are, of course, in the middle of an electric car explosion. This is the photo from the Tesla car plant. This is the photo of my German Shepherd, I basically get all my scientific thinking done when I'm going on dog walks with him. So he's, for whatever remains of my scientific productivity, he's responsible for it. But I've switched 5 years ago to electric cars, and I'll never go back. They're amazing. Essentially maintenance-free vehicles. So really quite phenomenal. And what's happening is that, I'm not the only person who's switching. The sales of electric cars have exploded in the United States thanks to high fuel prices. And the projection is that we're going to be seeing, this is a somewhat old graph, but now millions of vehicles sold worldwide. And the projection, if you take it out to 2040, is tens of millions, close to 100 million electric vehicles being sold worldwide. One of the drivers behind this is that countries are also effectively saying we no longer want air-breathing vehicles on the road. So countries around the world are declaring the end of air-breathing vehicles. Norway, which is a major oil producer, they will no longer allow the sale of internal combustion engine cars after 2025. And so I think thanks to the countries that are, have large populations with a diverse range of incomes who are insisting that you drive an electric vehicle, we're going to see an explosion of electric vehicles that are priced right and that are affordable. And I should also mention that the thing that's expensive about these vehicles is the pain point at the front when you purchase them. They cost 1/2 to 1/3 per linear mile to operate in a gasoline vehicle. And that was before the recent spike in gasoline prices. And plus you never have to go back to a gasoline station. So the 1/3 figures for Washington State, which is sort of a wash in hydropower. The half figures for the rest of the United States. But you can start to find, Los Angeles is also, it's not a country, but Los Angeles is also, and some other cities now in the United States, are planning to forbid the sale of fossil fuel cars, not this decade, but I think in the next. So that's coming. The last thing I should touch on, which is a slightly touchy subject, or can be touchy for some people, is food. Food is, the way that we currently produce food is a problem. This is, again, a solvable problem, but it's responsible for a lot of emissions. And we need to tackle this by rebalancing our diet, by altering the way that we produce protein, by making sure that the way that we produce food is renewable. And I know I hope I'm after dinner for all of you, so I can tell jokes about, I'm going to tell jokes about vegans because I am one, so I'm free to tell jokes of myself. But this is from the New Yorker, last Thanksgiving, making a joke about people who are persnickety about their diet, and then a lion looking very hungrily at a zebra right outside thinking, why am I eating a salad? And then, of course, the usual thing about vegans, at least by reputation, can't stop talking about the fact that they're vegan. And of course, I've just admitted to you in public once. But the reason why this is a big deal is that the difference between a diet that's moderate in meat and no animal source food at all is 5 gigatons of CO2 per year. This is the output, the entire greenhouse gas output of the United States every year. That's the difference in diet that diet can make. And as you can see, it's also, this number over here is equal to the entire output of the nuclear power plant fleet on Earth. So this is no joke. If you look at the amount of methane being emitted into the Earth's atmosphere, only a third of it from humankind is coming from fossil fuels. 2/3 of it is coming from agriculture. And methane is 30 times more powerful than CO2 as a greenhouse gas. So what world will we pass on to the future? I've got a meat thermometer stuck in the Earth to indicate that, we don't want to get it to the point where it's done yet. We still want it, pink on the inside. And so this is a question of paths, as we've discussed earlier, or in fact, really one path. Where will we stop on that path? And that's the choice that we now face. And that the scientific community has done its best to inform policymakers how to make that choice in an informed manner as possible. And with that, let me conclude and take any questions you might have. Thank you so much for your attention. So questions for me? Yes, please.
So I noticed on one of the graphs that you had the likelihood of different scenarios being adopted. So I was just wondering how you kind of quantify these likelihoods of policy scenarios.
So the question was, how do we quantify the likelihood of policy scenarios? One way of doing that is just assuming persistence of current trends and then asking, which scenario gets ruled out. That's one pretty logical way of doing it. Again, we were not supposed to be policy prescriptive in here, and we were strictly instructed not to get too far down the path of saying, picking winners or losers, but essentially presenting a very, judgment-free statement to the climate community about which one is preferred. Other questions for me? Yes, sir.
You mentioned something about if I trust airplanes, something about the model airplanes using. So I'm wondering if you could say something about the models used for the projections here.
Yes.
How they relate to this.
Thank you. So just to come back to the airplanes for a minute. So when Boeing built the 707, which is their first major commercial successfully jet aircraft, they built 70 models of the wings for that thing. The 777 had it's either the Dreamliner or the 787 or the 777 had one actual physical prototype of the wing built. That's all it took. And the compression by a factor of 100 was because they were able to simulate the plane entirely on a computer. So what's in these models are the equations that govern fluid dynamics. So it's equation of mass, it's a conservation of mass, conservation of energy, conservation of momentum. And then there's some terms on the right-hand side where energy exchange occurs, for example, with space, with the ground. And we run that set of equations essentially 3 times over. We run it for the ocean, for the atmosphere, and for ice sheets. And then the land is a bit of a mess. And we have a separate set of processes that govern sea ice. But that's what we do. It's physics-based, and we can test it against the observed climate record. And these models are imperfect. That's why we run 50 of them. So we're essentially trying to sort of flood the zone and look at models that are both insensitive and very sensitive to greenhouse gases. So we're not biasing toward one answer or another. Great question. Yes, in the back.
Do you know what are the projections for when human population will stop growing, and how much is that? How much is that something we should be thinking about, or is that like something that we don't talk about enough?
So the question was, what are the projections for human population and how are these folded into what we did? Some of these scenarios assume a world where we exceed 10 billion people. So in fact, one of them, I think, gets close to 12, which is a lot of people. The reason I think, in my mind, why I'm suspicious of those scenarios is that these pathways that I showed you are constructed. There's essentially a one-way transmittal of information from social scientists constructing these scenarios and then asking what the climate implications are, but there's no feedback from climate back on human population. And if you put that feedback in, I don't think you'd get to 12 billion people. But that is a factor here. As you might imagine, discussions of population and population growth are a little bit of a third rail. Because of international inequities in birth rates, and also coupled with greatly inequitable distributions of the benefits from the legacy of all the carbon dioxide that we've burned. So, this is how are you going to say to someone, we've enjoyed a great party, but we're shutting the door in your face, is effectively the challenge that we now face collectively in dealing with this problem in an equitable and just way. Great question. Yes.
Can you comment on, so eating meat,
Yes.
whether it's mostly the negative effects of the methane production by animals or the necessary production of fertilizer to grow the grains to feed the animals, or where it is the big contribution to.
That's a good question, and I'm afraid I don't want to speculate on the answer. There are actually three different sources of greenhouse gases for things like beef cattle. So they emit methane while they're maturing. They consume a lot of feed, which is produced with fossil fuel-based fertilizers, which, as we were discussing over dinner, leach off in the form of additional greenhouse gases to the Earth's atmosphere. And the third thing that's embedded in them is the energy that goes into the water to raise the animal, right? So 1 pound of beef equals 1,000 pounds of water. And in California, as you know, we spend 20% of our energy moving water from one place to another. That just putting water to the beef cattle is a commitment of energy. And many parts of the rangeland, that energy is not renewably sourced. But I'm sorry, I don't want to speculate on the answer about the partitioning. Great question, though. Yes, please.
So, you mentioned that the IPCC report, I don't remember exactly, but you say you did provide any policy prescription?
Yeah, the question is, did we discuss policy in the IPCC report? No, in other words, we're not saying don't warm the planet more than this. I mean, there's no statement in there like that. It says if you do that, here's what we think will happen.
No, I guess my question more is like, in your opinion, what, given the technologies available, like, what do you recommend the countries to do right now to take that action? Like whether they should pursue nuclear power options?
Great question. I think nuclear needs to be on the table, to be honest with you. We have something like 5,000 years worth of nuclear, if we were to use conventional nuclear technology, about 5,000 years worth of nuclear fuel to supply a large, significant portion of the energy needs of humanity. There have been some breakthroughs recently on fusion, which are promising, but still, there are jokes about fusion I won't tell here, but it's still always right around the corner. But we desperately need to make humanity, by hook or by crook, needs to make our global economy carbon neutral by 2050. And that's a very firm recommendation. And that, unfortunately, that's going to require really turning the ship of state around. Yes, Steve is pointing out, Steve Chu is putting in some questions. One of the questions is, the IPCC conclusions you quoted are phrased as if the geoengineering option did not exist. Could you comment on that? We did look at that issue extensively in this assessment. We started in the fifth assessment 7 years ago. We now looked at it quite a bit in this one. There are, I mean, in some sense, we're already geoengineering the planet. We are altering the planet in ways that are geologically consequential. And if somebody comes back and digs this era up 1 million years from now, they will see fossil records from what we did to the planet. But the question is really, can we, for example, reduce the amount of sunlight that the Earth absorbs and thereby cool the planet by essentially creating a parasol? And the IPCC did look at those options. There've been a number of reports assessing them. And the scientific community, although it was very reluctant to investigate them, is now actively investigating them. There are major challenges with keeping geoengineering going long enough. Because again, this is a you bucket, you bought it model. I mean, we're talking about geoengineering for centuries in order to cope with what we've done. So we did assess it. The scientific community at this point is, I'd say, agnostic about it. It does have, there are things like if you create an artificial volcano, that creates droughts. So again, it sort of exacerbates some climate justice issues that we talked about earlier. Second question was, can you compare uncertainties in climate models you described with unknowns in methane released by melting permafrost? Some of the models include crude, well, let's see. The uncertainties in the climate models are bigger than the effects of melting. The total basket of uncertainties in the climate models are bigger than the effects of methane being released by permafrost. They come from a variety of sources, including feedbacks from different parts of the climate system, including from clouds. Those feedbacks are bigger than the effects of methane. I know methane is a very, people worry about it a lot. The measurements that have been made in the Arctic indicate that yes, carbon is being released by melting permafrost, but at least the latest measurements I heard is that most of that carbon coming off the permafrost is being expressed as CO2, not as methane. So it may not be as big a deal as we previously thought. Thank you for those 2 questions from the online audience. I'm happy to keep going here. Yes, I see a question. Yes, please.
So, do you know what the impacts are of warming of 1.5 Celsius on poor countries, Latin America?
So the question was, what is the effect of warming by 1.5 degrees for poor countries? There are one of the things that we are seeing that is going to be pretty consequential, and this falls out of incredibly rudimentary climate models. So this is a very robust result, and you can also show it from theory. The storm tracks are moving toward the poles, and what they leave behind in their wake are regions that are drier and have greater drought frequency than they used to. So we're seeing this sort of front of droughts propagating up, from it's sort of expanding over a larger and larger portion of Central America, as a for instance. We're also starting to see it now propagate down into South America, and there's concern about what that's going to do to the Amazon, which is also home to many indigenous people who've been living off that land for thousands of years and will be greatly affected if the Amazon goes into a drought state. There's the Sahel, home to, I think, 250 million people, which is going to be drastically affected by increased drought frequency. And the other issue, of course, is this isn't a huge number of people, but people who are living in close to subsistence lifestyles on island nations that are very close to sea level. So earlier in my career, I did an experiment on the Maldives, which is an island, a set of atolls in the middle of the Indian Ocean. That's just a meter, less than a meter above sea level rise. And they're now starting to have to construct artificial islands to see whether or not they can survive. So these are countries where these are not wealthy countries. So they will all be drastically affected by 1.5 degrees. Great question. Yes, please. Right. So it's a great question. So the question is around the fact that batteries contain a lot of rare earth metals, precious metals. And this is, there's now quite literally an international, I wouldn't call it arms race, but minerals race, because a number of countries have figured this out and are starting to make deals with other countries that have large reserves of these minerals. We will definitely have to have a very robust recycling program to make sure that all these materials are recycled as effectively as possible from batteries, make sure the batteries have a longer lifetime. And, you know, who knows? I mean, electric vehicles currently seem like the easiest way of getting a clean fleet, but we may end up using, I mean, it's hard to predict. Japan seems to be very interested in hydrogen. It turns out to be kind of hard to produce renewably, but hydrogen has the advantage that the fuel cell in the car is a much simpler object and is perhaps a good deal more renewable in terms of its recycling properties. It doesn't have some of the same disadvantages as batteries. But yeah, this is going to be, I mean, there's I've forgotten, Steve, there's like a soccer ball sized of rare earth inside a Tesla battery. Now imagine scaling that to hundreds of millions of vehicles per year. And you're talking about a very large mining operation. And I don't know how sustainable that is, to be honest with you.
I'd like to make a comment on that. Lithium in your trust is not as abundant as nitrogen. And there are many people, including my group, who are figuring out how to get lithium from seawater. Will increase the reserves by about 5,000. And so if we can get it to seawater, that's not to say we shouldn't recycle. And there are startup companies already and very serious concerns, and they're already, you have to build it into the new batteries, and this is being done now. People are beginning to design EV batteries so that they are recycled in terms of the lithium. The nickel and cobalt, there's not enough nickel or cobalt to do EV batteries in 80% of the fleet. It just simply is not enough. And so the other thing is to try to get away from nickel and cobalt, and that's been recognized. The rare earths, these are, cobalt especially is just, and even nickel, but the rare earths which are used in magnets and electric motors and things, it's very polluting. It's not that rare, but the mining is very polluting. So there's a lot of effort trying to do that, but in the end, we have to figure out how to get, so there's a resource problem. And so you're going to buy time. So sustainability doesn't mean sustainable. Sustainability to me means, can you buy 1,000 years, 5,000 years, and hope that the population goes from 7.8 to maybe peaks at 11, 10.5 billion, and then maybe goes down naturally as people get more educated. There's a natural population decline, one hopes, but these concerns about the resources are very, very real, and there's a lot of research being done to buy time, to buy at least 1,000 years. But beyond that, you know, it's going to be someone else's problem. But but these are great questions.
Yes, please.
So we've been talking about electrification, but it's still like centered around basically just working individual people. Why aren't we focusing on centers instead? I feel like this is a much more like resource that like not too much is better for resources altogether and also like in the long term maybe.
So the question concerns why the focus on individual vehicles as opposed to focusing much more on getting people to use collective modes of transportation, public transportation that's also renewably powered. I mean, I'm not a civil engineer nor a transportation engineer, so I can't really comment with any degree of expertise on why these choices are being made, but I do concur with you. And there are, I think my understanding is that urban planning is beginning to look increasingly with favor on undoing the model of making cities as car-centric as at least some of the cities in the US have become. And I know a number of cities in Europe have been actively exploring making them much more friendly, for example, to electric bikes, which are a great way to get around. So a great question, a great point. And we do need to think about how to make, also, of course, having electric vehicles sort of allows you to continue propagating sprawl. So we need to there are a bunch of issues around design of our urbanity that we need to solve in sort of one fell swoop, especially since the estimates are that over 70% of humanity is going to be living in cities by the end of the 21st century. So, now is the time to get that right. Great question. Yes, yes.
Is there any viable development of non-fossil airline?
Steve, do you know that this is a question about biofuels for airplanes?
I can answer this. But first, there's a lot of startup companies trying to think of battery, but it's only for very small local transportation. So it turns out fossil fuel, not fossil fuel, but liquid hydrocarbons are really very good. Now, there's been a recent breakthrough in the last year for the first time. Craig Ventnor's group, in combination with Exxon, I think Exxon was giving them the money, figured out how to increase the yield of algae, photosynthetic algae, about 4 or 5 times from what it was 5 years ago. And now within a factor of about 2, kerosene, jet fuel are very long hydrocarbon molecules. And when you make jet fuel from crude oil, a certain fraction, only a certain fraction goes to kerosene. The kerosene and diesel are the long chain ones, are the most valuable. And so if you can get photosynthetic biofuel to be within a factor of 2 of that, then you can offload a lot of the long haul industrial stuff that is very hard to do. The personal vehicle stuff, the light duty vehicles, electric or hydrogen will take care of. It's that long haul, fuel for 15 minutes to go 10,000 miles we don't have. So it's possible that photosynthetic generated jet fuel will become a reality in 5 or 10 years. Because for the first time, it's an earshot of being cost competitive. Cost competitive defined the less than a factor of 2, which when I was Secretary of Energy, it was about factor 6 away. So there's been progress. I just want to make a comment actually on something Bill said that may not have been fully appreciated. 2 things. Agriculture and food production is more than electricity production and greenhouse gases. Half of the arable land in the world is under cultivation. We've engineered that. If you put all the people and all the animals we eat on one side of the scale, and all the other animals of the world on the other side, we're 96%. We have geoengineered the world. If you want to talk about geoengineering, think of agriculture. Yeah. It has profoundly geoengineered the world. And we have to re-geoengineer agriculture, which is also possible and technically possible. And not geoengineer, but changing our tastes in food will have to change. Because if you just put dairy cattle and cattle, it's more greenhouse gas emissions than the United States total, or the EU plus Great Britain total, just beef and dairy cows. So it's profound. And that's, forget about the chickens and the pigs, just cows.
So there's a question from our online audience asking about temperature contrast. The contrast and the temperature contrast between land and the ocean, and that contrast depends on the answer to your question about how to simply relate the two is complicated because it depends on the degree of contrast between the two depends on how rapidly you're sort of driving the climate system out of equilibrium, in which case the contrast becomes more extreme. One of the, I mentioned that these numbers that I'm quoting, which seem like small numbers, like 1.5, 3.5 degrees Celsius, no big deal. One of the ways in which you can see that really acutely manifested is a phenomenon known as polar amplification, where the poles become, the North and South Pole, warm faster than the rest of the planet. This is something that was predicted by Suki Manabe, one of the 3 Nobel laureates this past year, using a climate model. It's now a very robust observation. And that contrast is gigantic. It's, for some of the scenarios that we're looking at, the Arctic will warm by close to 10 degrees Celsius. So it'll be just a completely transformed place from where it has been historically. And again, getting back to the question earlier, all the first residents of those areas that moved there, in some cases, tens of thousands of years ago, will be strongly affected by that change. Other questions for me? Okay, I see 2 more. Yes, sir, and then I'll come to you. Yes, please.
So if a young physicist, say, out of their PhD, wants to find a way to help coach the situation in one direction, where can I find good points of leverage? Do you think going into the science is where one should focus on, or more like industry developing technologies, or maybe finding some way to affect policy, maybe straying a little bit further afield from my
It's a great question. Of course, one that many of us who teach in the STEM field are fielding these days. I mean, I think I've made the point fairly clearly that we have to cut the cord between energy and carbon. And any way in which we can accelerate that transition, and many of the things that we need to do, we don't understand how to do just yet. So batteries, for example, are far from where we need them to be in terms of the energy capacity per unit mass. There's work that I mentioned underway on direct air capture. That's really beautiful and elegant solid state physics. There are lots of ways to contribute. So you either reduce the source on the front end or take it out. But those two things are really critical, and we need to solve them in a hurry. And this, especially direct air capture at scale in a way that's environmentally benign, but also operates at scale, is something we do not know how to do. And if you had to ask me, I don't think we need to do the climate science any better. I think we've delivered that message pretty effectively. Politicians are not going to suddenly wake up tomorrow if I add another decimal place to my answers to them. What we need are solutions, and we need them like right now. So yeah, I would urge those of you who are interested in engaging from any discipline, but especially from STEM disciplines, let's go after the root cause, which is the connection between energy and carbon, and cut that cord. Yes, sir.
The question that I had is in regard to humanity, and as an example, I think 2 years in the
pandemic, and it was extremely difficult to teach people how to vaccinate and how to get masks.
Yes.
Now projecting it forward, what we described this in hypothetical or
Yeah.
do you think that the critical issues we manage, are we ready to absorb this and get this message and act on this? What I really believe is maybe the fuel prices or the electric car or not needing the state enough. This might not happen. I think what we have to do is we have to convince 10 million people how to do this.
So the question is, how do you, this happens to be an area of some considerable expertise of mine. I have to say those of us working on climate change looked at COVID with some considerable alarm because of the reaction to scientific information that was being presented and some adverse reactions to that scientific information. I think I'll just speak personally. The conclusions that I have drawn are that it is very important to frame this as a hearts and minds proposition where you're reaching people through their value systems about what they regard as important to themselves, to their family's well-being, to their own sense of self, and to make the solutions, congruent with that sense of self-identity, so that they feel like doing the right thing is also doing the good thing is also good for their families and good for their communities. And this is one of the reasons why we've begun stressing the social development goals, which is IPCC jargon, but the benefits that flow along from solving climate change. If I were to lower the carbon dioxide level in this room by a factor of 2 right this minute, none of you would be the wiser, right? You can't smell it, you can't taste it, you can't feel it, you can't smell it. It doesn't, it's effectively invisible. But if you immediately, in the process of reducing the carbon dioxide, you get better public transportation, and you have more green spaces in cities, you have, if you're living in Asia, your respiratory health is appreciably better. Those are all immediate benefits, or nearly immediate benefits. And we need to, I think it's very important for us to message around what good will flow from doing this. We will live in I hope, a more just, a more equitable, and most definitely a healthier world if we, and this can be quantified if we make these choices. And so that's, I think, driving the message around value, around, not hearts and minds is kind of where I think we need to be. And this is for shoegazing physicists, this is definitely an interesting lesson to be learning, but it's one that we have to pretty much embed in the way we communicate. Yes, in the back.
Do you think we need central planning of sustainability? And if not, how the different pieces of the solution can work around each other?
Question is, do we need central planning of sustainability? This is something that I think Professor Chu has thought about deeply. We're talking about really radically altering the infrastructure, some pieces of the infrastructure in this country. For example, making our electric grid work with a very different set of both sources and sinks for energy in ways that I don't think can just happen by accident. We need to be planning consciously, coming back to the point earlier around replacing the legacy fuels used for aviation with biofuels. That's something that has to happen worldwide. There are lots of places where I think some central coordination would really help, and that fumbling our way through this is not such a smart idea. And so for this reason, the colleagues and I that are working on trying to figure out how to make our economy carbon negative are running life cycle analyses and systems analyses about how to get everything in the right place. If you want to store carbon dioxide into the ground, where do you situate the facility so it's over a geological formation where you can safely inject the carbon dioxide and it will stay there for a long time? If you need access to renewable energy, where are you going to get the hydro from? Where do you get the solar from? These things, and this needs to be thought through. Now, there are ways, I think, of doing it a little bit more intelligently than we did in the past because we've gotten, as a society, a lot more nimble. And the compute power that we have now is astonishing. So I think I'm optimistic that we can pull this off, but this is a major, major alteration to our infrastructure. And I think there has to be some element of it that is coordinated, because at the moment, for example, think about the inequities at the moment. We have an unplanned situation where many people in the middle of the country are reluctant to buy electric vehicles because they would immediately be stranded. And that's simply because we have not planned as a society for an equitable, for a systemic deployment of electric recharge facilities over many of the vast interstate systems in the middle of the country. And that's happened by accident, and it's preventing the adoption of electric vehicles in a big swath of the country. That's something that some thought would help solve. So, great question. I think we need to be a little intentional here. I hope I answered your question.
Bill, that was wonderful. Is there one more question?
Okay. Yeah. Thank you. Okay, so let me now turn. I'm turning to look at the question. Do you think? Okay, the question is: do you think there's value and promise in increasing the specificity of climate models so you can predict the effect of climate change on specific cities and localities? Is this feasible, and could it help with communicating benefits of climate action to the general public? We're getting there. We, as a climate community, just ran a series of experiments with models that had 3-kilometer resolution. And to put that in context, San Francisco is only 11 kilometers wide. So this is sort of like putting down a little, 4x4 sort of bingo board over the city of San Francisco and predicting the climate in each of the squares in that bingo board. Do I believe the answer is no? I think it's a great question. The climate community is trying to get there, but I think that the deeper issue, I don't think modeling is going to save us here. I think we have to get used to the idea that we have to make decisions under uncertainty, and we have to be very honest with the policy community that an ever bigger computer and an ever fancier model, they can't wait for the final answer. Infrastructure takes decades to fix. They have to make decisions under uncertainty. This happens all the time in the medical field. We just watched this play out in spades over the last couple of years, and we got through it. But we cannot wait for the perfect model or the world's largest supercomputer to get us out of this problem. I'm convinced. I mean, the computers that we have now are literally 1 trillion times faster than the computer that was used to win the Nobel Prize. That's amazing. But we still have some of the same, core uncertainties in those models that were examined by colleagues of this individual in the late 1970s. Those uncertainties have persisted for the last 45 years, nearly a half century. That's a long time. We don't have another half century to wait for climate models to get to, the final answer. So I urge us to start thinking about this as something where we need to get moving now. And we'll make mistakes, but that's better than waiting. I don't know how long you want me to entertain questions. I do see a question from a gentleman in the back. May I?
Well, maybe one more question.
Yes, you have the last question.
I guess as we get to a point where some people like the best or make the most sort of positive outlook in the future have certain negative effects on certainty. How do we convince people to start thinking about hardening our current ecosystems or current cities to a future where there are going to be negative effects of climate change? And how do we do that in a way where I guess people can be something? Because I feel like a lot of times we talk about like, hey, the end is coming. People tend to shut down a little bit. So how do we get people to start to understand that some of these negative effects are happening, and the best we can do in some cases is just prepare.
Well, So the question is, how do we begin moving to a mode of making sure that our infrastructure is more resilient? I'd say that at the moment, the efforts around this are pretty heterogeneous. So the Department of Defense is definitely thinking about this pretty seriously. Their port in Norfolk, Virginia is being seriously affected by rising seas. There are New York City thought very hard about this after their recent experience with hurricanes, and I started thinking about what to do with using artificial reefs as some sort of storm surge barrier. But this is very heterogeneous, and there are other parts of the country where people are literally having their streets flooded more than once a week, who are unconcerned about what this implies for their ability to stay put. So I don't have a great answer for you. I am happy to say that a number of major US cities have begun very systemic processes around action planning. So for Chicago, where I went to grad school, has a really excellent climate action plan that they developed with the University of Chicago. We're starting to see cities partner with the great research universities in their backyards to think through these plans. There are also a consortia of cities on both the East and West coasts that are thinking about this. A great example is in our backyard, something called BayCan, which is the Bay Area consortium around adaptivity. I'm getting the acronym wrong, but there is a consortium in the Bay Area that's thinking about this and is partnering with cities up and down the coast. So at least the East and West coasts are getting really serious about this, and that's good. So we'll see more of this sort of, forward-thinking, proactive planning as we progress into the 21st century. And on that hopeful note, I'd like to thank you all for letting me talk to you about climate science. Very much appreciate your questions, very thoughtful questions, and the dialogue that followed the talk. So I hope you all have a wonderful evening, and I hope we will have a much brighter future based on taking action collectively. Thank you.
Thank you very much, Bill. And thank all of you and also many people online for attending. There'll be a colloquium that Bill will give another part of the Hofstadter lecture tomorrow. It's at 3:30, correct? Yes, 3:30. And so you can come in person or you can join us online. But again, Bill, thank you so much for the talk. It's a wonderful talk. You can